The next speaker is Maciej Brzeźniak. I think it's the right pronunciation. He is ready for his presentation. I didn't get a short CV of this person, so perhaps you can spend, one or two sentences max on your background and then go into your presentation. So let's go ahead with Maciej.
Okay, hello. My name is Maciej Brzeźniak. I work for Brzeźniak Supercomputing Networking Center. Mostly I'm focusing on data storage and data management services and systems. I'm responsible for data infrastructure at PSNC. In my presentation, I would like to present you the initiative and project called National Data Storage. I'm trying to switch to the next slide. Okay, the presentation will cover a bit perhaps broader view on the which a little bit goes beyond what was discussed as far, and will be also mostly discussed in this conference, which is about the tightly integrated compute and storage. I will speak a bit on different things. I will show how we would like to, and how are we trying to address the full data lifecycle, scientific data lifecycle in the HPC and in storage. I will shortly mention HPC projects in Poland and mention two use cases related to the project I'm presenting. So if we have a look on this conference program, we mostly speak about the data handling during processing. So we had presentation, we'll have more on how we optimize data access while computing. What we're working on in National Data Storage is a bit going beyond this. We are aware that, and everyone here is aware that the volumes of data which are to be processed in HPC systems are much bigger than those who can fit into the very expensive, high-performance, well-optimized storage. So in the National Data Storage system, we try to address the full life cycle of the data, going also beyond the period of a given computing ground, but also of a given computing infrastructure. Typically, we buy the HPC storage together with the HPC system. What we're working on is a little bit what is in between. So where people migrate their data for long-term storage, and also from where we at while applying HPC models and also AI models, where are we getting the data from for feeding these processes? So yeah, we also are aware that before we can use data for computation, we must collect them, heal them, enrich them, and make them in a specific format to be used in analysis and computation. These processes has to somehow be systematized and also supported. And also, we are aware that data don't end their life when they leave the high-performance computing system. There is increasing trend in making the source, raw, or reference data available. It's even imposed by policies, especially, for instance, in the European Commission, we have a policy on making data long-term available. It's partially related to the FAIR initiative and FAIR principles, but it goes beyond. What is in our scope, what is in our under our influence, is ensuring the data access in several aspects. Data has to be technically accessible. I mean, protected, physically protected. There should be interfaces offered which are consumable by today's application, also will be consumable by future application. And we also have to support for migrating the data between the short-living infrastructures, because we have to be aware that HPC infrastructures, typically they are used for 3 to 5 years, while data has to be preserved for much longer. And also to be open to our users and ensure their freedom, we should support them for opting in their data and also opting out. These are the principles we're working around in the project. So to some extent, we borrowed some, or we tried to map some concept from the kind of soundy some years ago, a data lake model. We tried to apply the assumptions of the data lake model to the large scientific data. Of course, this involves addressing issues such as large data capacity, access and storage performance, and scalability of the overall data lake. But in this talk, I would like to focus on the data access stuff, and also what we are focusing on the project is ensuring data access, data reusability, and extendability of the system in terms of functionality we can run in the system, and also interfaces we can use to store and access data. It is important because the data which we store today will be must be exposed in future in using the interfaces which follow the industry standards and also technological trends. It also, to enable this, we must include some functionality into storage. Previous speaker mentioned on the trend of doing the compute in the coupling together this storage and computing systems. What we're trying to do while applying this model, we try to implement it within the data storage system, the functions that are bringing together compute and storage, but also are including the data transformation features and functionality within the storage system. Example transformation can be, in fact, applying appropriate format to the raw data while presenting them to the end user onto the application. Trying to switch to the next slide. So the ambition of the project is to provide a complete environment for data-driven science. Not going into details, which are like detailed features I mentioned before, but they're also collected on the slide. I'd like to underline that we would like to enable efficient processing of the data, which are stored in the massive data storage systems. It is part of our mission to provide HPC computing on top of the data. That's why this feature of the data lake is like in the center of the project we're presenting. The context for our activity is also provided by the fact that there are several HPC projects conducted in Poland. I'd like to mention two projects which are coordinated by PSNC. PraceLab is a project which is in a quite advanced stage. We're in the stage of delivering the CPU-based general-purpose computing power. The overall power is around 14 petaflop of conventional systems and around 1 petaflop of GPU systems. And the successor project will provide much more specialized computing facilities based on AI-oriented GPUs. This will result in additional at least 25 petaflops of compute power, but we assume that with the current market conditions, we can get even 50 petaflops or more. The project which is currently deploying the infrastructure provides these numbers of resources, this amount of resources across the country. As you can see, we were able to update and upgrade substantially the computing and storage capacities. However, as I mentioned, this is only the first step, and the GPU-based compute resources will be added to this, what was shown on the map. And also the storage focus NDS project will provide more storage capacity and features. So the overall numbers, I'm just showing them for reference. This is around 250 petabytes of tape-based storage and 250 petabytes of disk-based storage, with an accelerated storage based on NVMEs of the total capacity around 10 petabytes. The ambitious target of the system is to provide 1 exabyte of the storage capacity to the Polish academic and scientific environment. Maybe this slide is quite technically specifically focused, but I would like to underline that we are trying to build on independent software hardware stacks. In addition to the traditional software hardware stack, where we mostly use tape storage with the disk front end as a cache, we are focusing our work on software-defined storage based mostly on Ceph when it comes to the long-term storage. And also possibly it's one of the options considered MinIO for the AI, which will be suitable for AI workflows. In addition to this, we'll be using accelerated storage solution based on NVMEs and also on FPGAs as storage accelerators. So the project structure and scope might not be most interesting for you, but I would like to mention that organized in the 5 laboratories are the work on providing particular parts of the software stack, software hardware stack. So first of all, we provide these core services which enable file system, object-based and block-based storage, data storage and access. This area of work also includes purchasing and tendering for the infrastructure, which by itself is a challenge, as you know from previous presentations too. On top of these services, we will implement a set of services which are data-centric and data-driven, including backup archive service, very basic service as for data centers. We will provide an integrated stack for building the ELK environments, NoSQL databases, also other database engines. Important part of this is the solutions for data processing automation. We would like to support automating of basic data processing in the storage systems, managed in a model similar to, for instance, Amazon Lambda. We see also that a complementary to the specialized HPC storage as needed by users are environments where they could, in a systematic and supported way, work on preparing the data for to be processed, analyzed, and computed. They include sync and share environments, which are typical like provide typical workspace for users and researchers. Solutions for federated access across sites. People tend to share data between sites, especially within the scientific collaborations. And also, we plan to integrate within and tightly integrate on top of data storage system, the data science environments, data science applications, so that users can run applications such as Jupyter Lab or so, while in the same time using computing jobs which are transparently spawned using our HPC computing power. Because my time is limited, I maybe cover 2 use cases to give you an impression of what you're working on. One of the use cases is related to radio astronomy. It's directly related to the LOFAR project, which PCC is part of this project since several years. And for more than 5 years, we're storing the several petabytes of the LOFAR data within so-called long-term archive initiative. And what was going on also was where the proof of concept and tests of high-performance system-based processing of the data sets stored in data in the LOFAR archive. Challenges here are processing large data sets and also efficient data movement between storage system and compute systems. So based on these features we would like to, let's say, nicely integrate the Dcache-based data repository on top of the data lake, on top of the low-level basic storage services. And would like to enable fast data transfers using, from one hand, the proper software stacks and also a broad scope of the supported data access interfaces. And also, you would like to use efficiently typical for data technologies which are typical for data archives, such as Ethernet, bound with the InfiniBand networks, which are or interface to the InfiniBand-based clusters, which are typical for HPC world. I'm trying to switch to the second slide. Sorry. So the second use case, which is might be interesting for the Polish environment, is the use case related to Polish UV ultraviolet satellite system, which is one of the projects on the so-called roadmap for research infrastructures in Poland. Here again, we deal with large data sets. The specifics lies in the fact that these data sets are gathered in a very distributed way. The data sources are very intense, and in a short periods of time, they can produce lots of data. So the NDS-related features which we would like to exploit here is the ability to deploy a repository software on top of the data lake in a well-integrated way. And also, again, as in the previous case, the tight integration with the HPC resources, which could be transparently used for data processing, large-scale data processing, and also automation feature, which we could use in a standard, like offering a standard industry standard way, such as Amazon Lambda, so that some initial actions on data could be automatized and triggered, for instance, when the new data are coming to the system. So, in summary, NDS is a project which targets providing complete environment for data-driven science. So, we're from one hand implementing the vision or borrowing the vision of scientific data lake. On the other hand, we're trying to tightly couple the data lake with the computing resources. The project started this year. We are in the requirements, use case analysis, and architecture drafting phase. We are doing some pilots and proof of concept on the existing infrastructure. And we're preparing ourselves for purchasing the next stage infrastructure, which I presented before. Very next steps are the deeper discussion with end users, working out the details of the requirements, dialogue with the industry, which will offer us this software and hardware solution for compute and storage. And we're, of course, open for collaboration discussion. Thank you very much.
Okay, Maciej, thank you very much for your interesting presentation. As a Dutchman, I am very pleased to see that you work with the LOFAR guys. So how do you actually transfer the LOFAR data, which is quite a lot, to Poland? What speeds and feeds do you use?
So currently we've got a dedicated 10 gigabit link, so it's not like impressive for the HPC people, I guess, because here we're speaking about typical links on 100 gigabytes per second and so on. But please remember, this is a local network, while LTA, LOFAR network, is a very distributed one. And we have a constant feed. We could easily say we have a constant feed of data, which is sustaining the link. Yeah, that's the situation now, and we're discussing the next steps, such as upgrading the links, and also, as you perhaps know, the LOFAR resolution and data producing speed will be increased in future. So yeah.